Hi everyone, today I'll be doing a summary on the theory of hash tables. When we look at linked lists, we know that the average time taken for operations on linked lists would be ON on average, because you would have to traverse the whole list for an unsuccessful case. Whereas for a hash, on average, it takes about O1, and we will see why in the next slide. This is because a hash table is actually an array where we have something like this. So if your hash table is size n, and you have n slots, then this is essentially an array. So we know that the access time of an array is O1, and that is why an access of a hash table is much faster than a linked list, where for a linked list, you need to traverse each individual node. So what we are doing here is we are compromising our space complexity for our time complexity. And as you saw in the previous slide, because we have many hash slots, what happens is that there must be a hash function that will generate a unique hash for a given key, such that we can map each key to a hash slot. So for a given table size of n, what happens is that if I were to have a key, I would have to hash the key, and this will give me a hash value. And this hash value must always correspond to this key, meaning, let's say if I were to pass a few keys in and I pass this key, there's this very same key one again, I must get the same exact hash value so that the mapping is always unique. And this is how we will trace where the key is inside the hash table. So another point to note is that the hash function should distribute the keys given evenly. And what do I mean by that is that there must be a function that splits the keys such that the keys are not always clustered, to a certain hash slot. It should be such a case that when I were to give you two different keys, the probability of a key not being on the same slot is higher. So that is what we define by a good hash function. So for more information on hash functions, you can visit my GitHub page. Yeah. So there are many hash functions, and two of them are listed here. So more information on that on the GitHub page. Now we'll talk about close addressing. So on the previous slide, we talked about how we want our hash function, given hash function and a key. We want the hash function to map a key to a unique hash value. But there are instances where we have two different keys. So this is key 1, and I have another hash, and I have key 2. And what happens is that both of these gives me the same hash value. Let's say hash value here. And this is very possible. So in such instances, to rectify the issue, because so we cannot possibly have two keys in one box. So to rectify this issue, what we do in close addressing is to chain these keys. So the idea of chaining is akin to using a linked list. So say for an example here, in slot 3, we currently have the node 6 inside here. And what happens is that, say I pass a node 9, a key 9 here. And what I do is, when I apply the hash function, I get 3. So my hash value is 3, meaning 9 will map to slot 3. But because slot 3 already has the node 6, what I do is I chain another node such that the node can fall under the same slot, and that is why we call it chaining, because you are chaining multiple nodes together. And why it is called closed addressing is because you are closed under one hash address. So for whichever number of nodes, say let's say n nodes, it will all be closed under this specific address tree. So that's the idea between closed addressing. And one example here is given 100 keys and 20 slots. Okay, if I have 100 keys and I have 20 slots, on average I would have 5 nodes per slot, and this 5 is my load factor alpha. So alpha is just a way of representing how dense my nodes are per slots, or you could say how many nodes on average would I have on every slot. And now we look at some of the functions that we use for hash tables. So for close addressing, under insertion, this is just a snippet of the code. If you would like the code, it will be also on my GitHub page, and I will just briefly go through the insertion. So for insertion, what we always do is to always check for a duplicate here. And why do we check for a duplicate? Is because we don't want to insert duplicate keys into the hash table. And why is that so? Say I already have key 6 here, and I insert another node 6, and I insert another node 6. And you will realize that if I perform this operation enough times, and I insert a node 9, and later on, if I want to search if node 9 is in the hash table, what I have to do is I would have to iterate through all these nodes, which isn't going to help me with my time complexity, because why we use hash tables is because we want a faster way of accessing our keys. So by putting duplicates into our linked list, we are extending the length of the linked list. So that's why we perform a duplicate check. The next is a sanity check, and for very obvious reasons, because if our hash table size is less than 0, we cannot insert anything in the hash table because it doesn't exist. Okay, the next would then be to perform the insertion. So what we basically do here is how we would perform an insertion for a linked list. So this is standard insertion. I don't think I need to explain that because the video get a little too long, but that's the idea of insertion for close addressing. So the next thing for close addressing would be searching. For searching, what we do first is to perform the sanity check to make sure that the linked list, the hash table is greater than 0. So the next thing that we will do is to obtain the hash address. So given a key, say I want you to search a key. Alright, how do you know where this key exists or lie on the hash table? It will lie in the location hash, which will give you your hash value. So having obtained the hash value for a hash table size n, if my hash value is here, and I know that this is close addressing, I will have a linked list at this, a hash slot. So what I will do is I will obtain the head of the linked list, and then I will iterate through all the nodes till I find the target key that I'm looking for. And if it goes to null, then I will return null because the key doesn't exist. So the next thing would be deleting, and the concept of deleting is really similar to the linked list on how you delete an item in a linked list. And the idea of how the search would be done is how you would apply the delete. What do I mean by that is, given a key, again, I will get the hash value. So this is my hash value. With the hash value, I will then go to a certain slot in the hash table. and I'll perform the delete. So say this is my target that I want to delete. Then what I will do is I will set the pointer for the previous to the node after the node to be deleted, and then change the pointer for this, and I remove the pointer for this, and then what I do is I will read my target. So that's about it for deletion. Now next, the open addressing. So previously we discussed close addressing, and what we meant by close addressing would be that all the nodes that fall onto the same hash value will be closed within that hash value. So for open addressing, what it means is that the key is not closed within the address. It can be found on other hash slots that may not correspond to its hash value. And how do we trace that? It will be through certain type of probing methods, which we will discuss in the next slide. So the idea of open addressing and close addressing differ quite a bit. So if you notice here, alpha must be less than or equal to 1. And what do we mean by alpha less than or equal to 1? For hash table size n, okay, you have say n elements or keys. Alpha is equal to n over m. That's what we said just now. You have alpha is equal to m over n. So like what we said just now, if you had 100 elements and you had 20 slots, your alpha would be 5. That would be your load factor. So for open addressing, if I say alpha must be less than or equal to 1, it must mean that this implies m is strictly less than or equal to n. And when n equal n, then alpha equal to 1. So any value, when n is more than n, alpha will always be less than 1. And this differs from the close addressing that we saw just now, because for close addressing, right, m can be, m can be, how do I write this? M can be greater than n, and m can be m can be greater than 0, and m can also be greater than n. And I hope you get the idea here, where there is no restriction on the value of m, because alpha can take on any value for close addressing. So that's the idea. And you see here, when there's a collision, we do a probe to get the next location which we insert the key. So I'll discuss that in the next slide here. Okay, for the purposes of this summary, I'll just discuss linear probing. If you're interested in the other types of probe, you can visit the GitHub page. So given this hash table here, I have 1, 2, 3, 4, 5, 6 slots. So the size of my hash table is 6. Let's say that the hash function that I'm applying, meaning when I want to get my hash value, it will be such that the hash function will do this arithmetic. So key mod size of the hash table. So key mod 6. Or rather, you start from index 0, 1, 2, 3, 4, 5. So the hash will apply arithmetic modulo key mod 6. So I will just step through the whole idea, starting with insertion, search, and then delete. And we will examine how this linear probing will work. So now say I give you a key equal to 0. we know that 0 mod 6 equals to 0. So 0 will be inserted here. Maybe I should change the color for easier visualization here. So now, this is the first insertion. Now, I give you a key equal to 6. So 6 mod 6 is 0, right? And we know that the key 0 is already inserted, yet you still must put key 6 into hash slot 0, and this isn't going to work because your load factor must be less than 1. So each slot can only take up one key. And what this means is that we need to source for an alternative location for key 6. And when we do linear probing, what we do is we will add 1 to the value of the key and then apply the same arithmetic modulo. So what we do is on linear probe, we will do 6 plus 1 mod 6 and we get 7. Sorry, we get 1. This is 7. And what happens is that now key 6 will be mapped to the hash slot 1. And it's seen here. If I were to give you a key 3, and if we do the modulo 6, we get 3 also. So key 3 will be mapped to 3. So that is insertion. So the idea of a probing is to apply a certain type of technique such that you can get the next position that you should insert the key to, and you will repeat this process till the key is inserted or till there's no possible hash slot such that it means the hash table is full and you're not able to perform an insertion. Okay, for the idea on searching, so if I want to search for key 0, what I will do is I will apply the hash function on key 0, and that gives me hash slot 0. So that's where 0 will be. But if you want to search for a key that was linearly probed, say key 6, then what will happen is if I apply the hash on key 6, I will get the hash slot 0 here. And what happens is that the key 0 exists in hash slot 0, index 0. So what happened is that that is not the key that I'm looking for. So I will linearly probe. So this will be the same path traveled as the insertion path. So I will go to the next slot. So when you linearly probe on search, you just add 1 to the key and you apply the hash function. So you get hash slot 1 and 6 exists in hash slot 1. So that is the that will be your search being successful. So say if you want to search for a key, say if you want to search for a key 6, 12, key 12. So if you do 12 mod 6, you will also get 0. So you will also start from the path, hash slot 0. You will then move, you will linearly probe such that you will get hash slot 1, you will see key 6. And then on the second linear probe, you'll come here. And you will realize that, or the algorithm will realize that this is an empty slot. So if it is empty, what will happen is that it will break out of the function and return not found. Why would it do that? Is because if 12 did exist, then 12 must have existed in this position here. So the fact that it does not means that 12 does not exist in that position. That's why. So that is for the idea on searching. And for the case of delete, so say now 12 is inserted here, and I want to delete key 6. So what I will do is, the same idea as the path that I'll travel. I will apply the hash function on the key 6 to get 0, and then I will travel here, and then I'll linearly probe, and then I'll realize that the current key in the hash slot equals to the key I want to delete, and I'll perform the delete operation. So unlike the close addressing, for close addressing, when we delete, if this is the target, I will do this, right? But this is not the case for open addressing. For open addressing, what happens is that we will use a flag to indicate the node is deleted. So what I will do is I will do this. So I am telling I'm indicating on the hash table by putting a delete flag so that the algorithm knows that this node is deleted. And why do I do that? So the example is as such, or it's an example that to illustrate why. This is because if I want to do my search and I want to search for 12 modulo 6 is 0, I will go here. So keep in mind 12 is already inserted for this example. I go to 0 and then I linearly probe. So 12 plus 1 mod 6, and that will give me 1. So 13 mod 6 is 1. I will go here. Now, if we were to just do the normal delete as in, blanco the thing, then what will happen is this will be a blank cell if I were to just delete the node as it is. So if it's a blank cell, then, from the discussion just now, the algorithm will break and it will return not found. And that's not what we want. What we want is for it to recognize that this is a delete flag and it is not an empty node. And if it's a delete flag, what happens is that I will carry on the probing such that I'll reach 12. So, 12 will be successfully found and the algorithm will return found. And how do we deal with delete flags like this? So how we deal with delete flags like this is we will perform the insertion onto such nodes when we encounter such nodes. So say I want to insert, key 18. So 18 mod 6 is also 0, and we know that this is taken. So when we linearly probe, we will come here. And when the algorithm sees the delete flag, what happens is that I will just perform the insert here to get 18. And once I perform the insert 18, I will remove the delete flag. And that is how we do the delete and insertion for the open addressing. So if you're interested in the code, it's also on my GitHub page. Before we end the video, we will have a look at the practice question. So we are told, given a load factor 0.5, alpha equal to 0.5, you know that alpha is equal to number of elements divided by hash table size. And we are told each key takes up 1 word and a linked list node takes up 2 words. And we are then asked what is the total space requirement for closed addressing. And for closed addressing, we know that, or rather we are letting the hash table size to be n. If my alpha is equal to 0.5 and 0.5 equal to m over n, then m is equal to n over 2. So it means that I have n over 2 linked list nodes inside this hash table. So if I want to find out how much space it is going to take, I just need n over 2 times 2, which is n. And that is just for the linked list node. And we must remember that each of these is a pointer that will point to a linked list. We must account for that as well. So, if indeed I'm going to have a hash table of size n, and I need a pointer to a linked list node, and I'm going to use a some structure for it, say a pointer that takes up 1 word, then what happens is that I will have n pointers. and then the total space will be equal to n plus n pointers, which is equal to 2n. So the total space that I will be taking up is 2n. And now, if the same amount of space, the second question, if the same amount of space is used for open addressing, what is the load factor? So I know that I have m equals to n over 2, and my space is equal to 2n. So, because a key takes up one word, then the elements itself in the open addressing will just be n over 2. And what happened is that I want to know, what is the load factor. So load factor is always alpha equal to m over n. That means n over 2 divided by 2n. That will give me 0.25. And that will be the load factor for open addressing. So you can repeat this process for other load factors as well. And if I'm not wrong, if you increase the load factor from 0.5, 1, and so on, you will start to realize that the load factor or this open addressing alpha start to increase. Has this statement by me out. And with that, we have come to the end of this summary. So thank you for your time. If you would like to have the code from the slides or the summary in the markdown, it will be on my GitHub page that I'll put in the link below. Thank you.